We are continuing on here with the Unit 7 Day 3 note, and we're talking about asymptotes. In particular, this video is going to be dealing with horizontal asymptotes, which we're going to start kind of referring to as the limits at infinity, which is really what these asymptotes are. They're not like vertical asymptotes where it's a restriction and your function cannot cross it. What the horizontal asymptote does is describes what happens to this function as x gets really, really large, approaching infinity or negative infinity. So again, just to kind of review, horizontal asymptotes are going to tell us about the end behavior of your function. And this is really important because a lot of people hear the word asymptote and think, oh, I have a horizontal asymptote. I can't make the graph cross that. And it can cause problems if you try and make your graph go around your horizontal asymptote somehow. Near the origin, which doesn't necessarily mean real small numbers, it can mean anywhere other than as x is approaching infinity. The graph absolutely can touch the horizontal asymptote, cross the horizontal asymptote. That could happen many times, in fact. So don't worry about not being able to touch the asymptote like with a vertical asymptote. It definitely can. So what we're going to do with a horizontal asymptote is to look at what our curve is doing as x approaches infinity, and that's plus or minus. We're going to look in both directions. Now, with horizontal asymptotes, the really important thing here is to understand this one limit. It's the limit as x approaches infinity of 1 over x, and that limit equals 0. You can think of this graphically. You can look at, say, the function 1 over x. So we can think of this graphically if we did a little sketch of this function. This is the very rough graph of 1 over x, but you see as you get bigger and bigger, as x approaches out infinity out this direction, the y values are approaching 0. And that's also true as x approaches negative infinity. It comes from the bottom. So you can think of this graphically if you're thinking about the function 1 over x, or you can just think of it numerically. If you take 1 and divide it by an enormously big number, it's going to get smaller and smaller. And eventually you'll get to such a big number as you tend towards infinity that 1 divided by the number will be essentially 0. So that's the limit that's really important to understand. And we're going to do horizontal asymptotes. The same rules from last year are going to apply, but we're going to look at these as a limit as x approaches infinity. This is a really nice review of your limits material for sure. So what we're going to do is think about that one special limit, the limit as x approaches infinity of the function 1 over x, and the idea that any polynomial can be rewritten factoring out the term with the highest degree from all other terms in the polynomial. So that highest degree is going to be really important, that we're going to be looking for the highest degree in the numerator and denominator of our rational functions. So we're going to evaluate the limit as x approaches infinity of our function if we get a value k. Sometimes we won't get an actual number. Sometimes the limit as x approaches infinity might be infinity or negative infinity, and then that's not an asymptote. But if it is an actual value, some real number, then that line y equals k is our horizontal asymptote. So we're going to find the horizontal asymptote by finding the limit as x approaches infinity of our function. Okay, and this is really just formalizing kind of the math terminology and math notation that you guys didn't necessarily use in advanced functions when finding the asymptotes, but we can use that now because we do have that limit notation. So I am going to evaluate the limit as x tends towards infinity of g at x. So this is the limit that I want to evaluate to find the horizontal asymptote. And I know you guys are looking at this and saying, oh, don't we just take the coefficients? Isn't it just 1 over 3? It is. but this is how we do it in a more formal mathematical way using the limit notation. So this is the limit as x approaches infinity of x squared plus 4x plus 1 over 3x squared minus 4x plus 5. And here I'm going to factor out the highest degree of x, which is an x squared. So I'm going to factor that out from the top and bottom. So I get 1 plus 4 over x plus 1 over x squared over x squared, and then 3 minus 4 over x plus 5 over x squared. Okay, I'm going to reduce the x squareds. Remember that I'm keeping the limit notation until I'm actually evaluating here. So I have 1 plus 4 over x plus 1 over x squared over 3 minus 4 over x plus 5 over x squared. Continuing this, running out of space a little bit here. So I'm going to continue this up, and now is actually the step where I'm going to evaluate the limit. I'm going to not necessarily sub in x equals infinity because we can't do that, but I'm going to evaluate the limit of each of these individual pieces when x tends towards infinity. So here, 1 plus the limit as x approaches infinity of 4 over x will be 0. And the limit as x approaches infinity of 1 over x squared likewise will be 0. And then on the denominator, we get 3 minus 0 plus 0. Same thing. The limit of each of those little pieces of our function, because there's an x in the denominator, will be 0. So then this is 1/3. My horizontal asymptote is y equals 1/3. Now again, is this something that you're going to need to do every time? No, but it isn't nice to see that this really does come from taking the limit of the function. So you're taking the limit of the function as x approaches infinity, and that tells you what's happening in terms of the end behavior of my function. This is the chart which you guys have seen for sure from advanced functions. If the degree of the numerator is less than the degree of the denominator, the horizontal asymptote will be y equals 0. If the degrees of the numerator and denominator are equal, you will have the horizontal asymptote be the coefficients of those two equal degree terms. So if it's an x cubed and an x cubed, or next to the 7 and next to the 7, whatever it is, if those degrees are the same, the horizontal asymptote ends up being the coefficients of those two highest degree terms. If the degree of the denominator is less than the numerator, so the numerator has a bigger degree, you maybe have a quartic over a cubic, we don't have a horizontal asymptote at all. That function will go off to positive or negative infinity depending on the values of the function. So another thing that we should look at is test values. Again, this is just kind of a little bit more detail of what we would be doing here. We want to know whether this function is approaching that horizontal asymptote from above or below. So we're just going to test large positive and large negative values. So maybe f at 1,000 and f at negative 1,000, and we're just going to see what those values are and compare it to the horizontal asymptote. If the function at a very big positive or negative is above the horizontal asymptote, then we're just going to state that it approaches from above. If it's below, then we'll just state that it approaches from below. For our original function from the example, we had, just writing this out for you again, g at x equals x squared plus 4x plus 1 over 3x squared minus 4x plus 5. And I'm just going to test, say, g at 1,000 and g at negative 1,000. So I'm going to just take my calculator, sub in those values. So 1,000 squared plus 4 times 1,000 plus 1 divided by minus 4,000 plus 5. So here I get that this is approximately 0.335 for a big positive number. And we remember that the horizontal asymptote we found was y equals 1/3. So this is a little bit bigger than the 1/3. If I do that same thing, and I say use negative 1,000, and substitute that in, here I'm going to get about 0.331. So the first one, sorry guys, I typed something in wrong to my calculator. That's why I don't like all the test values. So that's above and this is below. So again, we're going to be summarizing each of these using appropriate limit notation. So I'm going to say this is the limit as x approaches infinity of this guy's g at x. This equals 1/3. Now this is a little bit kind of fuzzy notation, and I've seen this some places and I haven't seen it used others, but I like it, saying that this approaches 1/3 from above. So we're just going to use that plus to mean from above. And the limit as x approaches negative infinity of g at x, it also equals 1/3, but from below. So if we're going to add that plus for approaching from above and the minus for from below. So really today, this whole lesson is the same as the horizontal and vertical asymptotes that you've already done, but just adding in kind of a limit notation summary to use the proper calculus form.